Hello everyone, let's look over chapter 22 amines. The amines are derivative of ammonia. So NH3 is ammonia and designated as primary, secondary, or tertiary. When you see alkyl group on nitrogen, that's primary amine. When you see two alkyl groups on nitrogen, that's a secondary amine. Three alkyl group on nitrogen, we can call tertiary amine. Trigonal pyramidal nitrogen atom of the amines carries a partial negative charge on its lone pair. So lone pair can function as a base or nucleophile. For example, functioning as a base. So proton acceptor. So you can generate ammonium salt. And then functioning as a nucleophile. So lone pair attack to carbon to generate ammonium salt. Nomenclature of the amines. IPAC nomenclature allow for two different ways for naming primary amine. Number one, name alkyl group ending in YL followed by suffix amine. So now there are two carbons, the ethyl, YL, ethyl, add amine. Also, this one, substance, isopropylamine. This one, cyclohexyl amine. So name alkyl group ending in YL followed by suffix amine. Second, more complicated primary amines are named as alkan amine. Alkan amine. There are names same as alcohol, but suffix amine is used instead of OL. So in this case, the base chains, there are 7 carbons, and then you can see C2 and amine, then 2 heptane amine, then 2 substance FC4 and 6. So 4,6-dimethyl 2-heptane amine. So you need to see configuration. So you have to check atomic number. So first priority has nitrogen, second one, this carbon, third one, this one. So 1, 2, 3, so R groups. So 2 R, this one, first priority, this carbon, second priority, this one, third one, that one. That's counterclockwise. That's S, but you can see hydrogen to the front. So you have to change S configuration to R. So 2R, 4R dash 4,6 dimethyl to heptane amine. And third one, use the term amino for the group as a substance. As a substance, you can put number 1, 2, 3, 4. You can see amino group FC4. So 4 carbons, butane. Drop E and add OL, that's alcohol. So 4 amino butanol. Also, this is benzoic acid. So 1, 2, 3, 4. SC4, you can see amino group. So you can write down 4 amino benzoic acid or para amino benzoic acid. You can use one of them. If amine is directly attached to aromatic ring, the parent name is aniline. You need to memorize common name. So this is aniline. So name of this compound. This one is aniline. So 1, 2, 3. You can write down 3-chloroaniline or meta-chloroaniline. This is aniline. So you can put number 1, 2, 3, 4, 5. So we need to follow alphabet order. So this one alkyl group, fluoro groups. So 5 ethyl, E first, and 2 fluoroaniline. Naming secondary and tertiary amine. So number 1, name alkyl groups followed by amine suffix. Use di and try if there are more than one of the same groups. So this is 1 carbon, 2 carbons, 3 carbons. So you need to follow alphabetic orders. So ethyl, methyl, propyl, amine. So 2 carbons, 2 carbons, diethylamine. 3 methyl group, so trimethylamine. Use di-tri suffix prefix. Number 2, find carbon parent chain and use suffix amine. Smaller groups attached to amine should be named as an alkyl group with N locant. So find base chains. So 1, 2, 3, 4, 5, 6. 6 carbons in base chain, hexane. And then you can see on nitrogen, you can see methyl and ethyl. So N ethyl, apparently order, N methyl, 3 hexanamine. And then C2, you can see chloro. So 2, 2 dash dichloro. Also configurations as C3. So number 1, priority, number 2, number not here. Number 1 correct, and number 2, number 3. So that's counterclockwise, that's S configuration. Let's check solubility. Amines with fewer than 5 carbons are typically soluble in water. So primary and secondary amine can intermolecular hydrogen bond. So on nitrogen, you can see 1 alkyl chain, that's primary amine. On nitrogen, 2 alkyl chain, that's secondary amine. You can see 3 alkyl chain on the nitrogen, that's tertiary amine. So primary, secondary amines can intermolecularly hydrogen bond, have higher boiling point than tertiary amine. So primary amine, 50 degrees Celsius. Secondary amine, 34 degrees Celsius. Tertiary amine, 3 degrees Celsius. So when you check molecular formula, that's C3H9N. All that the same, but different. You can see different boiling points. Amine are stronger base than alcohols and ethers. Amine can be readily protonated by strong and weak acid. For example, this is acetic acid. That's weak acid. pKa of acetic acid is 4.76. So deprotonate to generate protonated amine. That's pKa is 10.76. So it's used to have a general idea of pKa value of protonated amine. This one. So you can check pKa value of ammonium ion of several amine. So pKa of most alkyl amine conjugate acid are between 10 and 11. So most alkylamine, 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 conjugate acid, conjugate acid, conjugate acid are between 10 and 11. 10 and 11. And arylamine are less basic than alkylamine. The lone pair is delocalized. So this one arylamine, arylamine, arylamine. So can you see lone pair delocalized. So less basic. What it means, we can see low pK values. For example, this lone pair, the localized lone pair is less available for protonation to make resonance structure. And rearrangement, we can get more resonance structures. So arylamines less basic than alkylamine. Lone pair is delocalized. The presence of the electron withdrawing group also decreases basicity. So now can see arylamine, same, but you can see para position. This is electron donating group. There's no substance CN, that's electron withdrawing group. So presence of electron withdrawing group also decrease basicity. So in this case, you can see pK value is 1.7. Electron donating group pKa is 5.3. So decrease basicity. Lone pair of amide, the CO and R2, that's amide, is not considered to be basic nucleophilic. It's extensively delocalized into carbonyl group. So rearrangement to generate cation on oxygen. Okay, preparation of the amine. So preparing an amine from the alkyl halide. So primary amine can be made from, this is the primary amine, one alkyl chain on nitrogen. Primary amine can be from alkyl halide. This is alkyl halide in two steps, step 1 and 2 steps. The carbon skeleton is expanded by 1 carbon. So there's a 1, 2, 3, 4, 5 carbons. After reaction, you can see 1, 2, 3, 4, 5, 6 carbon. So expanded by 1 carbon when you use alkyl halide to generate primary amine. So preparing an amine from carboxylic acid. So this is carboxylic acid. So amine can be made by converting carboxylic acid to amide first, and then reducing the amide with lithium aluminum hydride. So when you use excess lithium aluminum hydride as second step water, you can get amine. Carbon skeleton is unchanged. So 1, 2, 3, 4, 5, 6 carbon. After reaction, 1, 2, 3, 4, 5, 6 carbon. It's same. Also, you can generate aniline from the benzene. This is the aniline. Okay. So from the benzene, you can use nitric acid and sulfuric acid to generate this product. And in uh, reduction, you can get aniline. You can use hydrogen with platinum, and you can see also two steps. You can use iron, zinc, tin 2 chloride, and uh, acidic condition and a base. So amines are good nucleophiles, readily undergo SN2 substitution with alkyl halide. So ammonia react with alkyl halide to generate quaternary ammonium salt. And then proton transfer step, finally you can get primary amine. Okay, let's focus on monoalkylation. Monoalkylation is difficult because nitrogen becomes a better nucleophile as it picks up alkyl groups. So after getting primary amine, this primary amine react with alkyl halide again to generate uh, quaternary ammonium salt. Quaternary ammonium salt react with ammonia to generate secondary amine. Secondary amine react with alkyl halide again to generate quaternary ammonium salt. And then proton transfer step to generate tertiary amine. And then you can get quaternary ammonium salt again. Azide synthesis, conversion of alkyl halide to azide. Alkyl halide, you can use sodium azide to generate azide product. So followed by reduction to yield primary amine. So one alkyl chain, one nitrogen, that's primary amine. There are two ways. You can use hydrogen, platinum, and you can use lithium aluminum hydride and water. This is a better way to make primary amine than trying to monoalkylate ammonia. When you look at the mechanisms, azide ion function as a nucleophile and attack alkyl halide, expelling a halide leaving group. And lithium aluminum hydride transfer hydride ion to the alkyl azide. Nitrogen gas expelled as a leaving group, giving an amide ion. And proton transfer step can get primary amine. Also, Gabriel synthesis of primary secondary amine from phthalic imide. This is phthalic imide with potassium hydroxide to generate potassium phthalic imide. Potassium phthalic imide is alkylated by SN2 reaction. So you can get alkylated phthalate imide product. The last step generally employs aqueous acid or hydrogen to liberate amine. So you can get primary amine, and after neutralize, you can get primary amine too. So preparation amine by using reductive amination. Reductive amination, ketone or aldehyde, in this case ketone, is converted to imine. When you use acid and ammonia, you can generate imine. And then reduce to corresponding amine. Add a hydrogen with a platinum metal. Then you can get primary amine. If reducing agent is present, imine can be reduced in situ to form amines. Reductive amination can be accomplished with a variety of the reducing agent. So you can use sodium cyanoborohydrate. Sodium cyanoborohydrate because it is selective for imine. So since sodium cyanide borohydrate does not react with ketone or aldehyde, it can be used in situ during the imine formation and yield desired amine in one reaction synthesis. So for example, reduction amination can yield primary, secondary, tertiary amine when you use ammonia and sodium cyanide borohydrate can generate primary amine. When you use primary amine, you can generate secondary amine. When you use secondary amine, you can get and tertiary amine. Overall, there are three options to produce primary amine. Primary amine. So you can use Gabriel synthesis, like halide and hydrogen, and you can use azide synthesis, sodium azide, and alkali and reducing reagent. And then you can use also ammonia and sodium cyanide borohydrate. So primary amines can be used to obtain secondary and tertiary amine. So after getting primary amine, you can generate secondary amine, tertiary amine by reductive amination. Also, you can do alkylation to get quaternary ammonium ion. So we call amines converted to amide. From amine converted to amide with acyl chloride. Two more of amines are required. Acylation of the amine can be used as protecting groups. Consider how to perform monobromination of aniline. This is aniline. So if aniline is directly brominated, polybromination observed. Can you see polybrominated anilines? So amino group is too powerful of activating groups. So we need to do amine must first be protonated as amide. So you can use acyl chloride to protect it, nitrogen. And then bromination, you can get para-brominated product. And then amide hydrolysis, you can get product. Brominate product. So aromatic amines can now undergo Friedel-Crafts direct release. This is aromatic amine. Amine with loose acid catalyst. This is loose acid catalyst to generate this intermediate. So ring is deactivated. To achieve the ring alkylation, first amine must be acylated. So aniline react with acyl chloride to generate a product. This is protected amine. And then alkylation and hydrolysis, you can get para alkylated product. Like alcohol, amines can serve precursors for the synthesis of alkene. Excess metal iodide. Excess metal iodide will convert one amine to tertiary ammonium salt. 1, 2, 3, and 4. Tertiary ammonium salt serve as a good leaving groups. Strong base causes E2 elimination. Silver oxide is commonly used. Silver oxide commonly used. So when you see the mechanisms, hydroxide deprotonate to make terminal alkane. So this process is called Hofmann elimination. So Hofmann elimination gives the terminal alkane reduced selectively. So let's substitute the alkane. The reasons are statics in anticoplanar conformation hinders attack at the most substituent site. Nitrous acid unstable and has to be generated in situ in order to regulate an amine. So nitrous acid loses water to form active electrophile, nitrosonium ion. So sodium nitrite liquid HCl to generate nitrous acid. So nitric acid is protonate to give oxonium ion. So oxonium ion loses water to give a nitrosonium ion. So nitrosonium ion is extremely electrophilic. So immediately react with an amine as soon as it forms. So 1 and 2 alkyl group attached to the nitrogen secondary amine yield and nitrosamine. Nitrosamine. You can use sodium NO2, Na, NO2, and HCl. When you see the mechanisms, you can generate nitrosonium ion, and then nucleophilic attack, proton transfer. Finally, you can get N nitrosamine. So primary amine yield diazonium salt. This is diazonium salt. So this process is diazotization. Diazotization. So when you look at the mechanisms here, so primary amine attack nitrosonium ion, resulting ammonium ion is deprotonated. And after proton transfer step and loss of the leaving group, finally you can get product. Let's review reaction of allyl diazonium ion. Alkyl diazonium salts are extremely unstable and decompose to form varietal product. So we might use aryl diazonium salt. Aryl diazonium salts are a bit more stable, synthetically versatile as covered in next sections. So aniline liquids NaNO2 and HCl to generate aryl diazonium salt. Diazonium salt. Then you can get variety of the product. Then the major reactions are reactions of the aryl diazonium ion with a copper salt to install halogen or cyano group on the ring. So aryl diazonium converted to aryl halide and aryl cyanide by using copper 1 bromide chloride iodide copper 1 cyanide. Sandman reaction is part of a multi-step sequence to install carboxylic acid on a benzene ring. So step 1, when you use nitric gas, sulfuric acid, you can get nitrated product. Number 1. And step 2 and 3, you can see reduction NH2. And step 4, you can use sodium, Na, NO2, and HCl to generate aryl diazonium salt. And then finally, you can use copper cyanide and H3O positive to generate carboxylic acid. So aryl diazonium ion serve as precursor for installing fluorine or hydroxyl group in the benzene. So it is good to know reason. So when you add HBF4, you can generate fluorine. H2O and heat can generate OH here. Diazonium ion can be replaced by with the hydrogen atom. Diazonium ion 2 hydrogen when you use H3PO2. This is useful when amino groups is needed on the ring temporarily to take advantage of the activating the directing effect. So when you see the amine here, so there are 2 steps to generate product. Step 1, you can generate aryl diazonium salt. So N2 positive, Cl negative. And step 2, you can remove this part. Diazonium salt also serve as electrophile attacked by activated aromatic ring. Process is called azo coupling. Pyro is a simple aromatic heterocycle. This is pyro. So 2, 4, 6 pi electrons undergo electrophilic aromatic substitution faster than benzene. Substitution SC2 gives a more stable intermediate. And you see the mechanism, you can generate carbocation, and rearrangement, you can generate resonance stabilized intermediate. And then you can see substitution SC2 in pyro. Imidazole is also aromatic heterocyclic. It's found in natural occurring compound. So 2, 4, 6 pi bond, pi electron. And also here 2, 4, 6 pi electron. So pyridine is 6-membered heterocyclic. 1, 1, 2, 3, 4, 5, 6, and then heteroatom. That's pyridine. So lone pair on nitrogen is not delocalized, this one. So pyridine is a weak base. So pKa is 5.3, weak base. This is pyrimidine. There are 2 nitrogen on aromatic ring. Pyrimidine is similar to pyridine. It's common moiety in biological molecule. So pyridine and pyrimidine can undergo electrophilic aromatic substitution reactions, however, usually with low air. Thank you for watching video.